Hello, everyone. We're on 1.3 Combining Transformations Part 1, uh, review of transformations of functions. So we've done translations, so vertical and horizontal translations. We've done reflections in the x-axis, in the y-axis, and we've done stretches, horizontal and vertical stretches. Okay, let's put it all together in this lesson, and in the next one we'll do this in two parts. Okay. First, here's a giant chart summarizing all the different transformations. So review the transformations of the function y equals f of x. Y minus k equals f of x, or I prefer to put everything on the right side, but either notation is okay. Y equals f of x plus k. This is a transformation, a vertical translation. If k is greater than 0, it's a translation up. If k is less than 0, the translation is down. Remember, you have to say vertical translation 5 units up, vertical translation 5 units down. So you must be very specific. You can't just say translation 5 down. Okay, and then the mapping notation, very important. This helps you write new equations or new functions based on the transformations happening. So for vertical translation, we add k to the y value and the x value stays the same. For a horizontal translation, y equals f of x minus h. A horizontal translation is if h is greater than 0. Translations to the right, h is less than 0. Translations to the left. Remember, you have to be very specific. A horizontal translation, 6 units left. You cannot just say translation 6 units left. You can't just say translation 6 left. You have to be very, very specific. Horizontal translation, 6 units left. What does that affect? That affects the x value, and the y value stay the same. So we're adding h to the x value. Mapping notation, very handy. A reflection in the x-axis. Okay. Y equals negative f of x. So you're multiplying by -1. Essentially, you're multiplying -1 with all the y values, and the x values stay the same. So it flips it or reflects it across the x-axis, where the x-axis is your mirror line. Y equals f of negative x. Very subtle difference here where the negative is. It's inside the function f of negative x. This is a reflection in the y-axis. This time, x values multiply by -1, y values stay the same. So we're flipping across the y-axis, so left, right. So we're flipping across the y-axis where the mirror line is the y-axis. Okay, stretches. Y equals a f of x, a vertical stretch about the x-axis by a factor of absolute value of a. Okay, so you must state it as a vertical stretch about the x-axis by a factor of 1/2. A vertical stretch about the x-axis by a factor of 3. If a is less than 0, so we treat the factors separately, hence the absolute value sign. We treat the factor separate from the reflection. If a is also less than 0, so if you have a value, let's say a equals -3, the absolute value of -3 is 3. That's your factor. That's your vertical stretch factor. But it's also less than 0. A is less than 0. A equals -3. Then that -1 multiplied by the 3, that is a reflection in the x-axis. Okay, so two separate things going on. What happens with the a value? We apply it by multiplying it. What you see is what you get. The a value that you see in the function, you multiply it straight with a y there. Okay, y equals f of bx. This is a horizontal stretch about the y-axis by a factor of, okay, remember, b value, don't let this trick you. What you see is not what you get with the b value and the factor. The b value that you see is in the function that you're reading. So when you see the equation of the function in the correct format, that's the b value. But if you want the horizontal stretch factor, you must apply 1 over absolute value of b. For example, if the b value is 2, so b equals 2, what's the factor of the stretch? It's 1 over absolute value of 2. So it's 1/2. Okay, couple ways to think about this. I just like to keep it simple. What you see is what you get here with the b. When you do mapping notation, okay, for mapping notation, right? You take the b value and you say x divided by b, and you leave the y alone if it's just a horizontal stretch about the y-axis. Okay, that's mapping notation. Okay, the other way to do it is if you look at the factor and you multiply x with the factor, you get the same result. So x over b is x over 2, or the factor times x, they're equivalent. So there's two ways to do this when you look at the mapping notation. Okay, just remember, b value that you see in the equation, it's not the factor of the stretch. You have to apply this little rule here. Also, other thing going on, if b is less than 0, then the graph is also reflected in the y-axis. Couple other notes. We have to talk about the generalized form here, the general transformation model. Multiple transformations can be applied to a function using the general transformation model. So two ways to write it: y minus k equals af square brackets times b of x minus h, and then close those square brackets. The other way is if you add k to both sides, you put the k on this side. I prefer this because everything is on one side. It's up to you how you want to do it. Mapping notation. You can combine all the mapping together. Oh, I should go back here. So that is your vertical stretch about the x-axis. This is your b value. That's the b value, and 1 over absolute value of b. That is your horizontal stretch about the y-axis. This is your h value, which is your horizontal translation. This is your k value, which is your vertical translation. Okay, so all of our quantities there are represented. So also, if b is less than 0, that's a reflection. If a is less than 0, that's a reflection as well. We can combine all four into mapping notation as x over b plus h, comma, a, y plus k. Important here, when sketching a combination of transformations from an equation, okay, so I'll ask you, I'll give you an equation, and I'll say, sketch the transformation from original to new. Use the following order. Start with the original, start with stretches and reflections, and then any translations, and show the final graph. I like to think about SRT. That's stretch. Take care of the stretches first, then the reflections, then the translations. Another handy way to think about it is if you've done the math lab and the investigation, does it matter if I apply a stretch or reflection first when I transform a graph? If you did the investigation, you'll see it doesn't matter which order you apply the reflection or the stretch. I just say start with stretch because this is a handy acronym that will help you remember. Always do the S and the R first before you do the T, the translations, when you're applying transformations. Another way to think about it is, you know bedmass rules. Do you do multiplication and division first before you do addition, subtraction? Yes, of course. So stretches and reflections, if you look, stretches and reflections are all multiplication or division, right? So if it's a fraction like a 1/2, that's essentially division, but we're talking about multiplication and division. So you would apply those first before you do the translations of h and k, which are addition and subtraction. Okay, so that's another way to think about order being important. Let's do a couple examples, folks. Describe the combination of transformations that must be applied to the function y equals f of x to obtain the transform function. Sketch the graph showing each step of the transformation. So we're going to do this piecemeal, okay, step by step. First, we need to see what is going on here. So we're going to we'll follow the SRT rule, stretches, reflections, and translation. So do I see any stretches? Yes. What stretches do I see? I see right there. That's a equals 2. that's a vertical stretch about the x-axis by a factor. Okay, remember absolute value of a. So what you see is what you get with the a value, right? So by a factor of absolute value of a, which is absolute value of 2, by a factor of 2. Okay, so this graph, a vertical stretch by a factor of 2, what does that mean? I'm going to multiply. So if I go back up here, here's my vertical stretch. I'm going to multiply all y values by a. So in this case, the factor is 2, so I'm going to double every y value. So if I double 0, it's just 0. If I double 2, negative 2, that's negative 4. If I double negative 2, negative 4. If I double positive 2, that's positive 4. If I double positive 2, that's positive 4. Okay, this one I will draw just a dotted line, folks. Because we're part way there. Okay? All right, reflection, none, right? I don't see a reflection. A is greater than 0. So A is greater than 0, no reflection. Last one, translation. So this will be, we'll go from the dotted line one to the final one. I have a translation. So I'm going to translate. What am I translating? My k value. So remember, we're in the proper form. Y equals 2f of x minus 3. Well, that's my k value. And it's in the form minus k, right? So k equals, oops. Where's our general form? Right here, folks, sorry. Okay, the form is plus k, sorry about that. The form is plus k, so if I have a minus k, that means it must be a minus negative k to get a plus k, right? So let's take a look at this. So it has to be in the form plus k, right? So I'm going to rewrite it up here. Y equals af of b times x minus h plus k. Okay, so in this case, the k value is negative 3 because it's y equals 2f of x plus negative 3. And I'm putting it into this form so I can read the appropriate transform value. So k equals negative 3 in this case. K equals negative 3. How do we write this out? This is a vertical translation, 3 units down. Okay, so take our graph with the red dotted line. We're going to translate everything 3 units down. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and then this time solid line because this is the final transformed function. All right, there you go. Letter B. Y equals f of 2x minus 4. So do I have it in this form? I don't, because look at this. Look what's going on in the brackets. I need to rewrite this as this. Y equals f of, I'm going to factor out a 2, and I have x minus 2. Now, am I in the proper form? You betcha. I can read my b value. I can read my h value. Okay? All right. Let's start looking at what we got here. Any stretches? So we're going to do SRT, stretches first. Any stretches? Oh, I have a b value equal to 2. Okay, but we know for b value, the 2 is not the factor. Right? So here's our b value. Okay, b value. remember the factor of the stretch is 1 over the absolute value of 2. And so the factor is 1/2. How do we write that out? This is a horizontal stretch about the, hang on, horizontal stretch about the y-axis by a factor of 1/2. Okay, what does that mean by factor 1/2? Go back to this. Here's my b value. When I map it, I divide x by b, or I multiply x by the factor. It's the same thing. Okay, so in this case, the b value is 2. I'm going to divide every x value by 2, but not do anything to the y value. Okay, so let's apply this transformation first, and then we'll do the last couple. Okay, so I'm going to go horizontal stretch about the y-axis by factor of 2. So the y values stay the same. Okay, x values are cut in half. So 1, 2, 3, 4. I'm just going to go to 2. 1, 2, 3. I'm going to go to 1.5. Okay, this 0, I'm going to stay at 0. 1 up here, I'm going to go to 1/2. 1, 2, 3, I'm going to go 1.5. So here's my, oops, I'll do dotted line for this. Okay. Next one, no reflection. B is greater than 0, right? So B is greater than 0, no reflection. So I'm going to move straight to translation. Translate. H equals 2. Well, let's take a look. Am I in the correct form? I have x minus 2. I'm just going to look at this part right here. X minus 2. X minus h. I'm matching the signs. I'm matching the variable. It's in the correct form. So I just read off my h value with, which is h equals 2. Okay. H equals 2. Well, what does that mean in words? This is a horizontal translation 2 units to the right because h is positive, right? H is greater than 0. Okay, let's finish off the graph. So what I have here, a dotted line in red, I'm going to translate 2 units to the right. So this one, 1, 2. 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 Okay, and what do I got here? There we go. Okay, so step by step. So practice on step by step transformation based on multiple parameters. Okay, not just one this time. All right, example 2. Given the function y equals, given the function y minus 3 equals negative 1/2 times f of 1/2 times x plus 1, close those big brackets. Okay, lots of stuff going on. Describe using an appropriate order how to obtain the graph of the given function from the graph of y equals f of x. So if I start with the original function of y equals f of x, how do I get to this big mess right here? Big, big, big. Okay, how do I get there? Okay, I'm going to write our, what I like to do is I like to stack it. So I'm going to write our general transformation model y minus k equals a times f of b times x minus h. And then I'm going to write our transform function right below it, y minus 3 times negative 1/2 f of 1/2 x plus 1, close those brackets. Okay, why do I do that? Because then visually I can see top to bottom what the transformations are. So let's describe in order. So I'm going to go in order SRT. Okay, 1. Let's look at the stretches. Absolute value of A equals the absolute value of negative 1/2. So this is a vertical stretch about the x-axis by a factor, not by factor of negative 1/2, by factor of 1/2. Okay, the other one. I have a b value of 1/2, so b equals 1/2. So the factor is equal to 1 over the absolute value of 1/2, and the factor is 2. What does that mean? This is a horizontal stretch about, this time the y-axis, by a factor of 2. Okay? If I go back here, if the a value, the factor is 1/2, that means I multiply all the a values, all the y values by 1/2. If the horizontal stretch about the y-axis is a factor of 2, right, then I multiply every y value by 2, or I divide the y values by 1/2, which is doing the same thing. Okay? All right. 2. Reflection. What do we got? A is less than 0, right? Because A is equal to negative 1/2. That's definitely less than 0. So this is a reflection in the x-axis. Okay? Any other reflections? No. B value is greater than 0. No reflections there. Number 3. Translation. Okay, right here. This is the k value. Let me do this. This is the a value. This is the b value. K value. As it's written, it matches the general transformation model. So k value is 3. So k equals 3, which is a vertical translation 3 units up. Okay, don't just say translation 3 up. You have to say vertical translation 3 units up. Okay, h value. Okay, h, right? I'm not matching. It says x plus 1, x minus h. How do I make it match? I will say x minus negative 1. So h must be negative 1. Okay, if I'm just isolating this part in the brackets, right? So at h is equal to negative 1. What kind of translation is that? That is a horizontal translation 1 unit when it's negative to the left. Okay, don't be saying translation 1 left. You have to say horizontal translation 1 unit left. Be very, very specific. Okay, state the mapping for the transformation. So we're going to use the mapping notation that goes with this general transformation model. When I have x, y, and it's transformed into the new function, it's in the form x divided by b plus h, a, y plus k. Okay, when we write this out, let's fill in all the values that we've gotten from our new function. So x divided by b, what's b? 1/2. What's h? Plus negative 1. A is negative 1/2. y, and then k is plus 3. Okay, let's simplify everything. That's 2x minus 1, and that's negative y over 2 plus 3. There you have it. Next page. Okay, letter C. If f of x equals absolute value of x, sketch the original graph and the transform graph, y minus 3 equals negative 1/2 f of 1/2 times x plus 1 on the grid provided. So if this looks familiar, this is the example we just did before. So we're going to take a basic v-shaped absolute value function, and then we're going to apply all these transformations and see what happens. Okay, but let's do it. You can do this graphically where you plot. So I'm going to do this. In black, I'm going to plot our basic absolute value function. So here, in black. Remember, it looks like this. So okay. Okay, we can apply each of these 4 transformations, or 5. There's a lot. There's 2 stretches, vertical, horizontal. There's 1 reflection, and then there's 2 translations, horizontal and vertical. You can apply all 5, like each at a time in the correct order, and then come up with a new graph. Or let's be smart about it. Let's do it with our mapping notation, x, y. Let's pick some key points, 0, 0. 3, 3, negative 3, 3. We said our mapping notation is 2x minus 1. Oops, 2x, hang on. 2x minus 1, comma, negative y over 2 plus 3. Okay, so I'll do the first one like this. So 2 times 0 minus 1, comma, negative 0 divided by 2 plus 3. And that is negative 1, 3. Okay, that's just doing a little basic algebra to, or a little substitution operation to get your new coordinates. So here, 2 times 3 minus 1, comma, negative 3 divided by 2 plus 3. What happens there? That is 2 times 3 is 6 minus 1 is 5. And negative 3 halves, 3 is 6 halves, right? So that becomes negative 3 halves plus 6 halves is positive 3 halves, which is 1.5. Okay, I'll say 3 halves. 2 times negative 3 minus 1, negative 3 divided by 2 plus 3. That's negative 6 minus 1 is negative 7. And that's negative 3 halves plus 3. Well, it's the same as the one before. That's positive 3 halves. Okay. Now that we have these three cool points, first of all, we know there's going to be a vertical and horizontal stretch. So this thing is going to be stretched vertically, stretched horizontally about each axis. And then we're going to flip it around. We're going to reflect it, right? We're going to reflect it. A value is less than 0. It's negative 1/2. We're going to flip it down. So it's going to be a reflection in the x-axis. And then we're going to translate it. We're going to translate it what? 3 units up, 1 unit left. Okay? Let's plot these. Negative 1, 1, 2, 3. 5, 3 halves. 1, 2, 3, 4, 5. Okay? And then 1, 2, 3, 4, 5, 6. Negative 7, 3 halves. And then let's join those points. Okay? One quick thing to check. Where does our vertex start and end? Here's our vertex. It ends here. Vertex is one of those things where you're not the changing. It's a good reference point to check. Hey, where did my function get translated to. So if you notice, h equals -1, k equals 3. Well, -1, 1, 2, 3. That makes sense that the vertex is right here. Okay? All right. Example 3. Given the function y equals f of x was transformed to g of x equals -3 f of 1/2 x plus 4 minus 6. Wow. Answer the following questions. If the key point 8, -5 is on the original graph, determine the image point under the transformation of the graph to g of x. Okay, so I start with f of x. I go to g of x, apply a whole bunch of transformations. If I have the original point on f of x, 8, -5, right? So 8, -5. What will this point look like? Or what will it be? What are the new coordinates under this new function? That's what we're asking. Okay, let's do some mapping notation. X, y. What does it map to? Remember, it maps to this. X over b plus h, ay plus k. Okay, what's my a value? A equals -3. Okay, that's not only that's a reflection in the x-axis, but that's also a vertical stretch about the x-axis by a factor of 3. Okay, so a equals 3. B equals 1/2. Okay, if we do 1 over the absolute value of 1/2, that's our factor for our horizontal stretch. So it's a horizontal stretch about the y-axis by a factor of 2. Okay, but the b value is 1/2. Okay, we're just listing all the parameters. H, oh, this one, something's going on here. We got to rewrite that, folks. So I'm going to rewrite it like this. G of x equals -3 f of 1/2 x plus 8. Okay, and then minus 6. Okay, h value here. H value is, okay, remember the general transformation model. So let me write this over here. G of x equals -3 f of 1/2 x plus 8 minus 6. General transformation model is, I'm going to write it with everything on the right side, isolated from the y. So y equals a f of b times x minus h plus k. Okay, now that we see it that way, a is -3, b is 1/2. My h value is -8, and my k value is -6. Okay. Now that we have all our parameters straight, let's rewrite xy. X over 1/2 plus h, which is -8, and then a is -3 times y plus k. So that's plus -6. Let's simplify everything. That is 2x minus 8 and -3y minus 6. Okay, so over here, x, y, I have 8, -5, and I'm transforming to 2x minus 8, comma, -3y minus 6. Let's apply all these. That is 2 times 8 minus 8, comma, -3 times -5 minus 6. That is 16 minus 8 is 8. And that's -15 minus 6. Sorry. positive 15. Negative 3 times negative 5, that's positive 15. Positive 15 minus 6, that's positive 9. So this is my answer. So with f of x, the point 8, negative 5 transforms to 8, positive 9. Okay, last one. Is this the last one? Example 3? Sure is. Okay. It is, yes. All right. Okay. Point 10, 18 is on the transformed graph y equals g of x. So we're continuing with the same transformed graph. Determine the original point on f of x. Okay, so let's do this. So this is what we're doing. I'm going to rewrite it this way. So x over b plus h, comma, ay plus k. We're reverse transforming. So we have a point on the transform graph, 10, 18, this one. What is it on the original graph? So this is what we're doing now. Got to work backwards, right? So we have this. This is right here, 2x minus 8, comma, negative 3y minus 6. How do we go backwards to do that? Well, here's the deal. 10, 18. See a clue on how we get the x and the y value, right? 10 is equal to 2x minus 8. So 2x minus 8 equals 10. Let's solve it. So 2x equals 18. X equals 9. Well, look at that. Okay. 18 is equal to negative 3y minus 6. So negative 3y minus 6 equals 18. Negative 3y equals 24. Y equals negative 8. Okay. 9, negative 8. Okay. Original point on y equals f of x is 9, negative 8. Done, folks. See you later.